So I have a problem. Or maybe you have a problem. Because I think what's going on is y'all aren't taking me very seriously. And I think I know why. It's the 3D printing. I'm trying to make a channel about making my own lab equipment and teaching science to the masses. And I'm using 3D printing as one of my major tools. But a lot of people think of a 3D printer as being a hobbyist model maker's little toy, or at best in use for rapid prototyping, not for designing lab equipment. It doesn't help anything that I'm working with the Ender 3 Pro of Theseus, as opposed to the latest and greatest Bambu Labs Ubermensch with explosive decompression chamber and ray tracing technology. So what I'm saying is maybe we should design an experiment. Let's make a test to see whether or not this basic 3D printer can make laboratory grade equipment. What I've designed here first, I'm calling this one the burn through test. As you can see, is a series of divots in a little puck. Each of those divots is a different number of layer lines thick, from just 1.2 millimeter layer line all the way up to 5 of them being 1 full millimeter. I'm going to try putting different solvents in each of these and seeing whether or not they will burn through my 3D printed materials. The materials to test are classic PLA. Anybody, even your grandmother, can just print this at home. Slight step up to PETG. And then finally some TPU, which the first mod I made on the Ender 3 was to give it a direct drive so I could work with this stuff. I reckon this is our best candidate right here. The next test I've designed is going to be an environmental test. Each of these little splines is getting smaller and smaller, so that way, as it expands or contracts as I expose it to the heat or the cold, they'll start to snap, or maybe just melt away completely. That way we can run this through some of the more extreme environments that we'll find around our lab and see whether or not a 3D printed tool could actually hold up to those conditions. With that in mind, the way to do this experiment, let's go to the lab. So we have our little pucks, and the first solvent that I'm going to set up here is going to be sodium hydroxide. This is a strong base, literally just a sodium ion and a hydroxide ion. We have a 6 molar solution here that is common for use for pH adjusting around the lab. I'm hoping to get some kind of cool effect on the PLA. PLA, as we all know, stands for polylactic acid. Even though it is in a solid form as a plastic polymer, hopefully this strong base will have some kind of reaction and eat its way through it. I say hopefully. I know that I'm supposed to be supporting the idea that 3D printing is good for the lab work here. But let's face it, I want to see something get destroyed. We're going to test as extremist conditions as we can. Alright, filling each one of the pucks with just 100 microliters per divot. Making sure to get them all. And that's our 3 different sample materials filled. We're going to let this go. I'm thinking I'm just going to do each test for about 30 minutes. Do a quick little time lapse so I don't make you guys wait the whole time. And we'll check back in on it as soon as we can. Alright, not to spoil anything, but with the power of future sight, I can tell you, it's not just that things aren't looking like they're going from the time lapse. Nothing is happening. This sodium hydroxide had 0 effect on any of our 3 materials. It doesn't seem that a strong base at this concentration is capable of burning through any of these plastics or even damaging them in the slightest. So these are all washed off now as soon as I get them out of here. Gonna have them ready to go and examine, and it looks like nothing.
Even that thinnest hole is still completely intact. There was not any leakage on any of these, so let's step things up a bit. Let's move on to the strong acids. What I have here is a hydrochloric acid that, ready from the manufacturer in the bottle, it's come at a 30% concentration. That is very strong. This is not even diluted for use in titrations. This is straight up how labs will buy their hydrochloric acid. I'm applying it directly to our polymers for testing. Doing the same deal as before, just 100 microliters per sample. Getting them good and lined up here. Once again, there's no specific chemistry I'm hoping for here. I'm just going with the strongest solvents that I have around, trying to get things a good legitimate laboratory test to see just how they'll work. And bad news, everyone. This time lapse, you'll notice, is going by twice as fast. That's because the same thing happened again, and I didn't want to make y'all sit through it. There was no change at all. No change. During that time lapse, I just ended it by neutralizing everything with the baking soda. I'm going to add a little bit to the beakers just so y'all can see there is no liquid that has fallen into the beakers. This acid stayed completely contained. Yeah. Once again, even the thinnest holes in even our classical PLA, even our nice floppy TPU, no change. But there is still something stronger that I have. We're going to be pulling out the nitric acid next. And this stuff came from the manufacturer, the same as before, measured in percentage, a 70% nitric acid. And just so you can get some understanding of this, here on the pH meter, we have a negative 1.5. That's right, we have a negative pH. If you were ever taught that pH scaled from 0 to 14, well, you just learned something today. All right, pucks are lined back up. We still have the baking soda at the bottom, so hopefully when this burns through during the test, you'll be able to see it bubbling away in our neutralizing agent at the bottom. And if you can look close, we actually have our first change. The TPU is actually turning red as I'm adding the nitric acid. I'm kind of excited here. If it's going to burn away through the TPU, hopefully something great will happen during this test. Just get everything lined up. We'll still give it the full 30 minutes to see if it can do anything more than just change color. And begin time lapse. Once again with Future Sight, it's a double speed time lapse because nothing. I'm going to work extra hard to make sure everything's neutralized this time. Once again, I don't want to touch any of the 70% acid. Even for my channel and its normal shenanigans, you'll notice I'm working in a fume hood, gloves, and a protective face shield, and a lab coat. That's quite a get from the guy who started his channel by eating things he found in his lab. So, take everything we're working with here seriously. Alright, the damage. We have our first failure for the test. The TPU is severely discolored, and it did bubble outward like that, but TPU is known for its elasticity. It's made to kind of bubble out like that. So there honestly is no hole. Nothing actually got through the burn-through test for anything. I'm absolutely shocked. But we've got some pretty extreme environmental conditions, so maybe I can still show you guys something crazy. We're going to get out those environmental tests here in just a second, and we're going to dunk them into liquid nitrogen. Liquid nitrogen comes in at negative 196 degrees Celsius, or just 77 degrees above absolute zero. As we get it loaded up here, well, reload it, I forgot to show you guys the loading. So here we are. This is what they look like after 30 seconds. And stick them back in and give them the full appropriate 30 minutes. All right, and time lapse of staring at the doer. No, I'm just kidding. Skip right to opening it. Trust me, guys, this was a full 30 minutes. Pop everything back out for you. Try not to freeze my fingers. I hate trying to get things out of this liquid nitrogen container. You're able to slide stuff out the front, but then it slides back in as you try and touch it. The little flaps slip down. They're much better at holding things in than they are at letting them go. So, here's our first look. 77 degrees above absolute zero. And so here we are. The TPU is now completely solid. But nothing's damaged in the slightest. So I suspect that once we let it warm back up, it will be completely back to its normal state. Not necessarily sure, but we're going to set it aside and give it a second. The stiffer materials have had an interesting change. They've contracted enough that these smallest spines are bowed in. And I can kind of pop them back and forth, but they haven't disconnected at all. There's no actual breaks, just a slight deformation. So we'll check back in on them when they warm up too and see if they're able to stay together through the freezing and defrosting cycles. Five minutes later, everything survived both freezing and defrosting. So there's only one thing left to try, and that's the heat. We are going to put all of these samples into the autoclave. There is no way that they're all coming out of this one intact. I need something to just be completely melted and destroyed. And PLA will melt in a hot car, so there is no chance that we're surviving the sterilization power of the autoclave. Set it up. Try and push the buttons while looking through my camera for y'all. And once again, another 30-minute test. Pause if you want to check the temperatures. But the autoclave tape developed, so we're good. Okay guys, we're doing this one live. No voiceover, because I want you to be here as I do this. Because you're not going to believe the results. I did not believe the results, and we're actually redoing this one. This is the second time with the same exact outcome. Coming out of the autoclave, TPU, totally unscathed. Not that big a surprise. TPU is known for its durability. Awesome. The PET-G. Alright. Interestingly, all the connections are still intact. Nothing technically broke, but yes, clearly environmental damage. Our first loss for the PET-G. PLA is 100% autoclavable. The PLA that melts in my hot car went through the autoclave 100% intact. What the fuck? What the fuck?
So we said we were going to do an experiment. That means I can't say I'm upset by the results. I give you only data. PLA survived all of the conditions that we put it up against. Based off what we have here, it can take on the acids and bases found all around my lab and can somehow sit through an autoclaving that PETG could not. I suspect it took on all the steam, that being hot and steamed is what actually killed the PETG, and that's why it shriveled up like a little raisin. But none of those splines actually broke the way I thought this test would work. Meaning TPU was our only full failure. This is after a couple of days. I tried scrubbing off to see if that discoloration would just go away. No, it spread. And the whole thing suffered a bit of embrittlement, and those holes did end up eventually coming out. So like I said, I should be happy. This was actually what I said I wanted, to show y'all that a 3D printer was a valid tool for designing laboratory equipment. But I'm not gonna lie, I kind of wanted to see something melt or burn, or I wanted to see something go wrong. If anyone can suggest any more extreme laboratory conditions, feel free to let me know. But until next time, I guess, print in PLA and stay hungry.
If this channel gets to 100 subscribers, I will buy uranium and test 3D prints versus nuclear material.